Hello and welcome to Physics 12 Dynamics, lesson number 2, apparent weight. Today we will be talking about your weight and how you can change the way it seems. Before we begin with the apparent weight, we must talk about the weight itself. Weight is the force on you due to gravity. In other words, this is how hard you are being pressed into the ground. Typically, when people normally talk about weight, they are asking about your mass. In regular English, you ask about your weight, you answer in kilograms. But in physics, that is your mass. Weight in physics is the force you feel due to gravity. Remember, mass is measured in kilograms, while weight is measured in newtons. So consider yourself on Earth. What is your weight? Assuming that you are 60 kilograms and Earth's gravity is 9.8 newtons per kilogram. Your weight is simply how hard you are being pressed into the ground. This can be measured by your normal force. In this case, we know your normal force is equal to the force of gravity. The force of gravity is equal to mass times g, which is 60 times 9.8. Therefore, your weight on Earth is equal to 588 newtons. With sig figs, this is equal to 5.9 times 10 to the 2 newtons. This is your weight on Earth. But what if you were on the moon, where gravity is only 1.622 newtons per kilogram? In this case, your mass is still 60 kilograms, but gravity has now changed to 1.622 newtons per kilogram. Therefore, in this case, your weight, which is still equal to mass times gravity, is now 60 times 1.622, which is equal to 97.32 or 97 newtons. Being on a different celestial body with different gravity has changed your weight. But what about what you normally think when you think about the weight? What about your mass? What is your mass on the Earth? Well, in everyday life, if somebody asks, how much do you weigh? You may answer, 60 kilograms. This in physics is your mass. But what about on the moon? If you move to the moon, what is your mass on the moon? Well, your mass does not change depending on where you are. So your mass is still 60 kilograms. That is why referring to yourself and describing your own characteristics, mass is more useful than weight. Mass is only determined by how much matter you have in your body, where weight is also dependent on how hard you are being pulled down. Now we have seen that you can change your weight by leaving the Earth. But what if you cannot leave this Earth? Can you change your weight without leaving this gravitational field? Well, the gravitational field is simply an acceleration. So what if you add or subtract an acceleration by moving up or down? For example, if you are standing in an elevator accelerating at 0.50 meters per second squared up, would your weight change? How much would you weigh? Well, let's look. In this case, if you are standing in an elevator, you will still have gravity pulling you down. And you will still have the normal force of the elevator pushing you up. The difference here, though, is you are now accelerating upwards at 0.5 meters per second squared. If your acceleration is not zero, then it follows that your net force is also not equal to zero. So we cannot simply say the normal force is equal to the gravity. Here, we must state that the net force is equal to the normal force pulling us up minus gravitational force pulling us down. Remember, your apparent weight is found by your normal force, which is a measurement of how hard you are being pushed into the ground. So to find our normal force, we must find the net force plus the force of gravity. In this case, the net force is your mass times your acceleration. Your gravity is your mass times the gravity. Now, noticing we have our mass in both terms, we can take out m, and we are left with m times a plus g. Assuming our mass is still 60 kilograms, our acceleration is 0.5, and gravity is 9.8, we find our weight is now 618 newtons, or 6.2 times 10 to the 2 newtons. Therefore, if we are accelerating up, your weight has actually increased, and you will feel heavier. This matches with what you should know from real life. As an elevator starts to move up, you will start to feel slightly heavier than you actually are. What if the elevator is now reaching the top and the acceleration is negative? Well, in the same way as before, we have our force of gravity pulling us down, and we also have our normal force still pushing us up. However, in this case, our acceleration is down instead of up, so our net force is now negative. Again, we have our net force, which is now negative, equal to our normal force, which is positive, minus our gravitational force, because that is down and it is negative. Solving for our normal force, we find the normal force is now equal to gravitational force minus our net force. Our force of gravity is mass times gravity, minus our net force, mass times acceleration. Again, we can take out the mass that is in both terms, and we find m times g minus a gives us our apparent weight. Here our mass is still 60, gravity is still 9.8, and acceleration is still 0.5. Putting these numbers together, we find that our apparent weight is now 558 newtons, or 5.6 times 10 to the 2 newtons. From this, we can see that if you accelerate down, you actually have a lower weight. Finally, we have two questions here that you can try. First, if you are 70 kilograms, what acceleration do you need to weigh 300 newtons? Let's try. First, we will write down what we know. We know that our mass is 70 kilograms. We also know that we wish to have an apparent weight of 300 newtons. We can also understand from this question that the value we wish to find is acceleration. So first, we will draw a free body diagram, as with all force questions. We have the force of gravity pulling us down. We also have the normal force pushing us up to ensure we do not fall through the ground. Here comes the difficult part. The acceleration, we do not know whether it should be up or down. We can check by looking at what our weight should be and comparing it to our apparent weight. If our apparent weight is lower, we know acceleration must be down. If our apparent weight is higher, we know it must be up. But luckily, we don't have to do that. We can just say acceleration is moving up, and if it is not moving up, our answer will be negative. If it is positive, that means it is actually moving up. We have decided that the net force is up, so it will be positive. We also know that the normal force is moving in the upwards direction, and gravity is moving down. We wish to find which acceleration is needed, so we are solving for our net force, so we will leave it as it is. F net is equal to ma, which is equal to our apparent weight, minus the force of gravity, which is m times g. The acceleration we need is our normal force minus mass times gravity divided by our mass. We now have an equation with our unknown on the left and our right being populated only with values that we know. From the question, we can say our normal force is 300 newtons because that is our apparent weight. Our mass is 70 kilograms and gravity being 9.8 divided by, again, our mass is 70 kilograms. Plugging these numbers into a calculator, we will find we get 5.514 meters per second squared in the negative. So our answer is negative 5.5 meters per second squared up, or more simply, we can say 5.5 meters per second squared down, as shown in this answer. The second question, consider a box moving down on an elevator accelerating at 0.50 meters per second squared, and the scale says it weighs 443 newtons. What is the true mass of this box? This is a similar question to the one we have done above. Again, our first step is to write down everything that we know. From the question, we can see that the acceleration is 0.50 meters per second squared, and it states the elevator is moving down, so our direction will be down. We also see that the apparent weight of our box, or the normal force, is 443 newtons. We can also see from the question we want to know the mass of this box. So let's draw a free body diagram. First, we have our force of gravity pulling us down. We also have the normal force pushing us up. Here, we also have an acceleration of 0.5 meters per second squared down. Here, our acceleration is down, So that implies our net force is negative. And our net force is equal to our normal force pulling up and our gravity pulling down, becoming negative. Replacing the forces we can with the equations that we know, we have the net force is your mass times the acceleration. The normal force is the apparent weight from the question, and gravity is mass times gravity. Here we want to solve for the mass, so we will place both m's on the same side. Moving both m's over to the left, we have mg minus ma is equal to Fn. We have a mass in both terms, so we can pull the m out, and we are left with g minus a is equal to Fn. Our mass is equal to our apparent weight divided by gravity minus the acceleration. Here, our apparent weight was 443 divided by gravity, 9.8, minus 0.5 as our acceleration. And this gives us an answer of 47.63 kilograms, or written to our proper significant figures, 48 kilograms, as we have in our answer, 48 kilograms. That's all for apparent weight. Thank you for watching.